We're going to be talking about exponential functions, and as an additional handout this week, I've posted an article that gives a really nice overview of exponential functions and some of the practical applications of them. Make sure you read the article. What is an exponential function? An exponential function is one that has the variable x as the exponent. In the blue box, you can see what a general form for an exponential function will look like. A is the initial or starting amount. B is the base of the exponential. If it's between 0 and 1, it will represent exponential decay. If B is bigger than 1, it will represent exponential growth. And x is your variable, often it stands for time. Remember the vocabulary associated with exponents. The base is the big number, the exponent is the little one that's up high. The base tells you what number to use, and the exponent tells you how many times to multiply it times itself. As you see here, 2 to the 4th is 2 times 2 times 2 times 2, which is 16. On your calculator, you'd be looking for one of two keys, either a y to the x key, or the calculator on the right uses the caret key. In each case, you would enter your base number first, press the exponent key, and then put your exponent on it. What do exponential functions look like? Well, they get big very quickly. Notice 2 to the 6th is 36. 2 to the 8th is 256. And 2 to the 10th is 1024. Notice the amount of change between each of these is increasing. That causes a graph like this. Exponential growth will start slow, but then it quickly escalates. In the real world, you'll hear people say that population is often exponential. However, this isn't 100% true. Populations can't get bigger and bigger forever. Usually there's some point where that growth is going to slow down, usually because resources have been used up. So technically, population growth is more often logistic than it is exponential. But exponential can be a good model for a certain period of time. Now, if your base switches to being a fraction, look what happens now. You can see 1/2 to the 6th power is about 2/100ths. 1/2 to the 8th power is 4,000ths. And when you take 1/2 and multiply it times itself 10 times, you get an itty bitty number. And this graph shows you what exponential decay would look like. Very often, radioactive decay is the example that we use for this, where for every interval of time, the amount of the substance left reduces by half. One really important base that we use in mathematics is the base e. E is a number like pi. It's irrational. It goes on and on forever and never repeats. I put some digits of it up there. Where does this number come from? Well, it comes from taking the expression 1 plus 1 over n to the nth power and letting n get bigger and bigger and bigger, as you can see here on the right. Here n is 1, we get 2. When n is 2, we get 2.25. For the next one, we again get approximately 2.25. And you can see as I increase my n value, the numbers will get closer and closer to e. E shows up in a lot of places in the natural world, which is interesting. It's also used a lot in calculus. Your calculator is going to have an e to the x key. It's usually located on the ln button, which stands for natural log. And because it's printed above that button, you'll have to hit your second key before hitting ln. That'll give you a base of e, and you can put on the exponent that you want. Now, the last thing I want to cover in this section is shifting. There are some basic transformation rules for working with any type of functions, but we'll use exponential as our example. If you have a function and a number's added at the very end, like you see here, it's going to translate the function vertically up d units. So notice the orange curve in the middle here. I have 2 to the x power. By putting on a +3, you can see the whole graph has shifted up 3 units. Now, another important feature to notice of exponential graphs is they have horizontal asymptotes. So going back to the graph 2 to the x, my horizontal asymptote is y equals 0. But when I shift it up 3 units, my horizontal asymptote becomes y equals 3. Now, if instead of adding an amount, you subtract an amount, that's going to move the whole graph down that number of units. So again, if you take the orange function, f of x equals 2 to the x, and you put a -3 at the end of it, it shifts the whole curve down 3 units, including your horizontal asymptote. Compare that to horizontal shifts. Now the difference here is it's still addition and subtraction that causes the change, but it's inside of the function. Notice it's inside the parentheses. If you have a plus a certain number of units, that's always going to cause a horizontal shift left. So plus goes to the left. If you have subtraction inside your function, you're going to shift to the right. In this case, we have our orange graph. We have our horizontal asymptote, y equals 0. If I put the +3 inside the function, that's going to look like it being in the exponent, as opposed to being a big +3 at the end, which is the vertical shift. You can see that the graph has been moved left 3 units, which does not affect your horizontal asymptote. Start again at the orange function, but this time put a -3 on the exponent. Again, it's on the exponent, not sitting at the end of the function. And you can see the graph shifted 3 units to the right. Now let's look at some of my MATLAB examples. All right, first, how to evaluate some basic exponential expressions on a calculator. Now, I've got a graphing calculator emulator, but this works with any scientific calculator. You do not need a graphing calculator. Whatever calculator you're using, you would begin by typing in the base. On this calculator, the caret key, this upward pointing arrow, is the exponent key. You'll either have that caret or a y to the x key. Put in the exponent, press enter, and there's your answer. Exponents are allowed to be negative. Notice I get a decimal. This is because 5 to the -3rd really means make a fraction and move that 5 cubed to the denominator. And when you move it, you get rid of the negative. So these two statements are equivalent, and that's how the calculator got 0.008. All right, 2 to the 0 power, you're going to get 1. Anything to the 0 power equals 1. So usually you don't need a calculator for that one. When your base is a negative number, you have to be careful. Notice how I have parentheses around that base. I'm going to use the parentheses when I type it in, and that is the correct answer. -2 times itself 4 times is +16. Notice what happens if you leave off the parentheses. You get a different answer. This is because the calculator is following order of operations, and it does the exponent first, so it does 2 to the 4th, gets 16, and then negates it. So you want to make sure that when you're using a negative base, you do put it inside parentheses. This should be +16. And the last example, when you have e cubed, you need to find your e key on your calculator. Most calculators, it's going to be located on the natural log button, ln, but above it. So to use it, I'm going to hit my second key, then press that button. You can see it's created for me the exponent and even given me some parentheses. I put in my exponent, close parentheses, and we're going to get a decimal because remember, e by itself is a decimal. Okay, so that's just a few basic examples. Now let's look at some of my MATLAB stuff. This problem asks us to graph the function g of x equals 9/5 to the x power by making a table of coordinates. Sometimes my math lab might set up a table for you, other times you have to do this on your own on a piece of paper. So you can see off to the side, I have set up my table. And when I chose what x values to put in my table, I kind of looked at these graphs and noticed the x-axis really only goes from -3 to +3. So 5 values is usually enough, so I went with -2 to +2. In the middle section, remember, I substitute the -2 for the x. And then when it's time to evaluate 9/5 to the -2 power, I'm going to go back to my calculator. Now, you're going to want to keep that fraction in parentheses, and it doesn't hurt to keep the exponent in parentheses as well. So I get about 0.3. I'm just going to take one decimal place because realistically I can't graph better than that. So back to my table, I have the point -2 and 0.3. I do the same for all of the other x values. All right, I've calculated the other values I need, but I skipped one. 9/5 to the 0 power, I didn't bother putting into the calculator. Why? Because anything to the 0 power will equal 1. I'll take these values and now put them in my table. I've set up the coordinates of all of my points, and when I go looking at the graph, I'm going to look at the ones that are easiest to see, like 2, 3.2. That 3.2 is a big enough number that I should be able to recognize it. So if I go to my first choice, go to x equals 2, I have a negative function value. This can't be right. In letter B, when I go to 2, looks like it's between 0 and 1. Too small. When I go to 2, 1, 2, 3, oh, that looks good. Check the last one. At 2, I have the function crossing somewhere in between 1 and 2, which is also not correct. So the right answer is C. In the second example, we're asked to use transformations of the graph, and we're using f of x equals e to the x as our base graph to graph the given function. Be sure to give equations of the asymptotes. Use the graph to determine the function's domain and range. All right, my g of x I'm supposed to graph has e to the x minus 5. That minus 5 can be in one of two locations. It can be as part of the exponent, or it can be on the ground instead of up in the air. When it looks like this is a vertical shift, up or down. When it looks like this is a horizontal shift. Then you have to remember that when it's subtraction, it always shifts to the right. When it's addition, it shifts to the left. So based on my equation, I know I'm going to take the e to the x function and I'm going to shift it right 5 units, which is this choice here. Now I need to graph this function. In order to graph it, I would make a table of values like you saw in the last example. I've got my table of values set up, and again, I stuck with some values close to 0. G of -2 would be e to the -2 take away 5 power. If you take a -2 and you subtract 5, you get a -7. So when I go to my calculator and I get this. This is scientific notation. What the calculator is trying to show you is a small decimal. I know it's small because I have a -4 here. This is the same as 9.1 times 10 is what you should read when you see that capital E to the -4. What is 9.1 times 10 to the -4? I would pick up this decimal and move it to the left 4 places. So I end up with the decimal point. I fill in zeros in each of the spaces and my 9-1. So this is super small. Okay, I bring up my calculator and I jog through the next couple. But my math lab is going to ask you to graph this in a different way using a tool. So let's see that. When you get to the graphing tool, you're going to press the curve. And you can click a point anywhere for this first part, and it'll give you the basic shape of the curve. Now over here is where it's going to ask you to modify it. You can ignore the stretching or shrinking. We're only working with vertical or horizontal translations. And we said horizontal translation, we were supposed to shift our graph. And notice as I move the slider, I can move it to the left or to the right. Ours was supposed to shift 5 units to the right. So I placed my slider on 5 and you can see that the curve moved as well. I'm also supposed to graph the asymptote. So for that, I would click the line tool and it wants you to make it dashed. Now I choose 1 point on my asymptote and a second point on my asymptote, and you can see it's been graphed. Hitting save brings the graph into the question. Check my answer. Well done. Okay, back to the last couple of questions. I need to find the equation of the asymptote. I need to find the domain and find the range. Here's the graph of my function. Because the asymptote was not affected by this shift, it stayed at the x-axis. So my asymptote will be the line y equals. The domain of exponential functions, when you look at this graph, it keeps going all the way to the left to negative infinity, and it does keep going all the way to the right as well, to positive infinity. So the domain is everything. This curve stays entirely above the x-axis, meaning there are never any negative outputs. Therefore, the lowest y-coordinate I can find is almost 0. I need a round bracket because 0 is an asymptote. We're never really going to equal it, but we're going to get close. So that's why there's a round bracket. And then the y values continue rocketing upwards to infinity. Be really careful with your brackets in my math lab. And we're done.